So, as I mentioned earlier, there is the idea that if you have a problem that's not linearly separable, that you might be able to actually separate it linearly, but in a higher dimensional space. And there's actually a theorem about that, and it's covers the theorem, and that basically states that a complex pattern classification problem cast in a high dimensional space non-linearly is more likely to be linearly separable than in a low dimensional space. Okay, and so basically what the support vector machine does now is basically perform two steps. So first of all, you take your x, like the input dimensions or the input data, which has like this kind of wide of a dimensionality. You apply this non-linear function to basically increase its dimensionality up to this level, which are now our z values. And now we compute again the dot product of our z values with like this now increased number of parameters w to make a decision down, like with a one-dimensional decision y, so yes or no class kind of decision. And so this is kind of like the idea of what is happening. So what we will have to do is kind of like find these transformation functions which will go into those dual forms. And the cool thing is that there's a way to basically not have to compute the dot product between zt and zs, but to basically just apply a kernel to those two values to compute the similarity between two very high dimensional vectors. And so, like, how does this kind of covers theorem work? Well, basically, what we tried to find is this this transformation function that goes from R2 to R3. In this case, we choose this transformation function where basically x1 and x2 get transformed into a three-dimensional space. In this case, x1 square, square root of 2, x1, x2, and x2 square. So we transform this two-dimensional problem here that has no solution that is linearly separable whatsoever in a two-dimensional space into actually this three-dimensional space now that now has a linear separable problem, or like linearly separable solution with this hyperplane that has two dimensions, so that it goes through this three-dimensional space in this way. So it's kind of cool and like a nice illustration how this works. We're going to have one problem, the XOR problem, where we're going to talk about how, like, we're actually going to compute this ourselves to make it more illustrative. How this kind of works. But in theory, basically, if we apply this polynomial kernel in this case, or polynomial transform on our data points, we can now find this linearly separable problem. And but yeah, and so but now we have our data in this three-dimensional space where we have to compute more steps to identify like the similarity between two vectors, which can become a problem if it's too large of a dimensional space. But yeah, that's kind of like where the kernel comes in then. So so basically the kernel trick, which is important, is that, so we stated that the problem is nonlinear, and instead of trying to fit a nonlinear problem, we can map the problem to a new space by doing a nonlinear transformation using some basis functions. And these basis functions, for example, were these x square, x1, x2, x2 square, and so on. They could be anything. They could be very different like basis functions. So with this new space, we now can find a linear model that separates the classes, and basically it corresponds in the end to a nonlinear problem in the original space. So to separate the data in this three-dimensional space linearly, would, for example, correspond in this original space to a nonlinear solution, which basically could be like this circle here, okay? Or like something like that goes like this, right? Okay. So, and then, so basically, given a set of basis function, we can map X from a d-dimensional space to Z in a k-dimensional space. And the important part is that K is usually much, much larger than D, and possibly even larger than the number of observations that we have. Okay, and that makes the problem of like optimizing our parameters based off of the dimension of the input dimension, or the space where the data lives, a lot more difficult. So that's why we really needed to transform this optimization into an optimization problem that's dependent on the number of observations rather than the number of dimensions. And so the discrimination that we now have is basically always defined by these basis functions that we apply to any of the data points, and in the end that just changes our input vectors that are now basically reduced to this kind of dot product between two like k-dimensional, like we said that they have k-dimensions here, k-dimensional dot products or values here, and we need to now solve this, but instead of having to compute this dot product between these potentially really large and high-dimensional data points, we can apply a kernel, and that's kind of like the trick of using a kernel. And this kernel provides us with the similarity between the two vectors without having to compute this potentially really large dot product. So instead of mapping X to a new space, we only apply this kernel function to the original instances and get the similarity there. So that's kind of the idea here. And we're going to talk about like how these kernels look like, but yeah, and we have a bunch of examples here. So what would be the simplest kernel? Simplest kernel would be a linear kernel, so you don't do anything to your data, so in the end you have a dot product again, right? To compute the similarity between two unchanged vectors. So like that's why we are applying these nonlinear basis functions. So for example, in the polynomial, as a polynomial kernel, for example, we can now compute the dot product of the two instances that we get plus 1 to the power of q, and q could be anything like 1, 2, 3, 4, etc. In the case of 2, we have these basis functions. So we would have to go ahead and say, okay, for each of those data points, or like for my x's, I have to apply all of these functions, right? That's kind of complicated. But instead, we can just compute this, which in the end turns out to be like fairly simple. So we don't have to apply these transformations. We can just compute the quadratic kernel between two data points. And how does this look like? So well, basically, it allows us to find separation hyperplanes, or separation boundaries that are curved like this. So this is kind of like a polynomial of degree 2. Polynomial of degree 1 obviously would be a line again, so that's a linear function. Polynomial of 3 has more flexibility, could be in like an S-curve, and we can increase that up and up. Obviously, these basis functions would get more and more complicated depending on the number of, like the q here. What if q equals 1? Well, it's a linear function. Now what happens if we choose a different kernel? So I mentioned we can use a radial basis function kernel, which basically is something like it's similar to a Gaussian, where basically you define a center and then you kind of have like this curve around that center. And the closer two data points are, the closer they are together, so that means they are more similar and the value is larger. So computing the exponent, or like computing the radial basis function for two values that are very close to each other increases this value, and if they're very far from each other, it decreases it. So you can imagine this is kind of like a bell curve between two values. And now we have an additional parameter instead of the q before here, but this is a hyperparameter obviously. We have now a different hyperparameter which basically defines like how wide or how like rapid this radial basis function goes down. So if we choose this to be very large, we allow these two data points to be very far apart from each other, and if we make this gradually smaller and smaller, we can learn more and more complicated separation boundaries. Like in this case, for example, it's more like a linear, like a nice round curve with averaging out over across all these hyperparameters, these support vectors. And the smaller we make it, this S parameter, the more restrictive we are in the neighborhood of these parameters. And you can see the more and more complex it becomes, the more support vectors we require. Okay, so if we have this value very large, well, then we only need a few support vectors to define this problem. And if we go down and down, we need more and more support vectors that define this problem properly. And again, like, you can ask the question, so like, which one is the optimal solution in this case? Well, this one solves the problem accurately without any errors on the training data or on the data points that we have here. Neither does this. This one has 4 support vectors, and this one has 8 support vectors. So which one's the better one? This one, right? Because first we had the idea of like Occam's razor before, so we don't want too many like points to define our separation. But on the other hand, we just had another theorem that mentioned that the number of support vectors is actually directly proportional to the expected error on the generalization. So you don't want it to be too complicated. Okay? So again, S in this case is a tunable hyperparameter. Okay? And there are many other kernels, and for example, the sigmoidal kernel is one that sometimes is used, and you can try out different types of kernels in scikit-learn, for example. You can just call different functions, and for each of those different kernels, you will require to optimize different parameters. And I think the C parameter with the slack variables is common throughout them, but then you have, in a polynomial, you have to define the order of the polynomial, and in the radial basis function, you have to define this kind of like variance parameter, and so on. Okay? And as an idea of like how it looks like when you define specific kernels to your application or to your problem, I brought this example that I mentioned earlier, which basically is defined down here. So bag of words representations, as we had like one hot vectors, or like you have a million dimensional or 100,000 dimensional vector, and only a few of them are set to 1 because these words are actually in your document. You don't have to compute this complicated dot product between two documents, but you can actually just count the number of coincidental words between two documents, which is directly calculating the dot product between two very long vectors. So you can come up with any type of kernels if you have, for example, two graphs, I wouldn't even, like, you have like these variables that are connected somehow with each other. We're going to talk about this later on in the lectures. But how do you compute the similarity between those? Well, you can count, for example, the edit distance. You can count like other similarities between graphs, where, like, okay, how many overlapping locations do I have, and what's not overlapping, and so on. So you can come up with different types of kernels in many ways. I think there are, like, you can compute, for example, a kernel on like DNA similarities, which, well, again, would be very complex if you had to go through each pair separately and count those. Like, there's many observations. So DNA or proteins, for example, have very long representations, and you would need to count all of those, and the dot products are, like, expensive to calculate. So if you define kernels efficiently, you can compute this much faster. All right, so let's go through like one extensive example on how to actually apply a kernel on a simple data set, and then optimize the problem using the Lagrangian optimization. Okay, so for our problem, we choose the typical hard to or impossible to linearly separable problem of XOR. So basically, +1 as an observation is 0, and -1 as an observation is 0. However, for class 2, -1 is logical 1, and +1 is logical 1. We translate that into +1 and -1. So these guys are going to be +1s, and these guys are going to be -1s. Yeah, probably. If not, it's the other way around. As a kernel, what we apply is a polynomial kernel of order of 2. So we compute this for each of our data points. And our implicit mappings would be kind of like a 5-dimensional basis function, okay? But we don't have to compute that because we can compute that through the kernel directly. So what we have to do is we have to optimize this following function, so that our objective function in dual form, and C for simplicity is set to infinity, so we are enforcing linear separation. Okay, so we don't want to like have anything fall within the margin or on the wrong side. So we don't have to think about that for the moment. So we had in our like dual forms before, basically a sum over all the alphas. So we can write that down here, and alpha we know is dependent on the number of observations rather than on the number of dimensions. So we have 4 of those, and then we have to go from I to 4. So this is like going over the iterations of all the data points, as well as J to 4, because we have to like compute all the similarities between all the data points within our data set. And for that we have the alpha I and alpha j times yi, which is +1 or -1, and yj, and then we have kij, which is basically the kernel applied to xi and xj, so 1, 1, 4, 1, 1, 1, 2, 1, 3, 1, 4, then 2, 1, and so on. Okay, 2, 1, 2, 3, 2, 4, and 2, 2, and so we have to apply this like basically 16 times. So this then leads us to compute the kernel matrix. So like Kij is one entry in the kernel matrix, and the kernel matrix we can compute that real quick. So for the first one, we have x1. So x1 goes in the kernel, and x1 goes in the kernel. So it's a +1 +1 transposed times plus 1, so we have like 1 plus 1 is 2 as a dot product, right? So if we have like this vector times the vector transposed, so we calculate the dot product between those two, so that's 2 plus 1 is 3, the power of 2 is 9, right? And then we do plus 1 times minus 1 plus 1, so that's minus 1 plus 1 is 0, plus 1 is 1, square is 1. So K12 would be 1. And then the funny part is, or the nice part about this is that this kernel matrix is 9 on the diagonal and 1s everywhere else. Okay? So it's basically this thing here. Okay? So what I need to do now is I need to like insert these guys in this problem here, and if I do this repeatedly, basically what I can come up with is this linear equation system with basically the following values. So alpha 1 9 times alpha 1 minus alpha 2 minus alpha 3 plus alpha 4 equals 1. You can try that out, but it basically nicely reflects this matrix here where we have these diagonals. And what we do now basically is we take the first equation and reformulate it until we have alpha 1 on this side equals to etc. and so on, and we have 4 equations with 4 variables, and the optimal solution in this linear equation system is for all of the alphas it's 0.125. Okay, so 1. Alright. So what happens in our classification now is the following. So this is our original space where we really like have no chance to find the linear separation here, but if we transform this into the implicit space now, we find a separation that basically learns this, and we have a linear separation. This is only like 2 dimensions of this implicit space, but it's nice that we can see that we basically can find a nice separation. All Lagrangian parameters are not equal to 0, so that means that all of them are on the margin. So all of our observations are on the margin in this problem, and they're all actually support vectors. It is not linear separable in original space, but it is in the implicit space. And so yeah, with these values down here now, we could compute the W0, and we can compute the weights and so on. We can make decisions now based off of that. All right. To kind of round this up, I would also like to mention that support vector machines are in the basic case only 2-class classifiers, so they only have an optimal solution in a 2-class problem. So this cannot be expanded to a multi-class problem unless we apply our usual tricks, which are the like one class versus all other classes trick that we discussed before, or we apply the like one versus one class trick in this case. So where we have like depending on the number of classes we have, many different support vector machines, and we would choose the class or the class that we identify where the data point ends up to be furthest away from our separation hyperplane. Okay, so we wouldn't choose just the sign, but we would choose the maximum value of these discriminative, hyperplane differences. So that like we had one slide where we said we only need to compute the sign of like on which side of the separation hyperplane the data point ends up on, basically plus or minus. But if you want to work with multi-class problems, we actually have to also know the distance to the separation hyperplane, because otherwise we wouldn't know which class to choose again, right? And there are obviously like a couple of different problems with that, with these one versus all or one versus one. First of all, you have to compute many support vector machines in this case, for example, and we have to compute OK squared, so like K squared many discriminants, and like it becomes more and more complex in the number of classes that we have. So support vector machines are great for like a certain kind of problems, but the moment that these problems explode with respect to number of classes, number of input data, these support vector machines are becoming less and less viable. So you can imagine if you have a problem that has millions of data points, I would not start off with a support vector machine as a first trial solution, because the optimization, it tries to find the optimal solution, but it might take forever to do so because it's so many data points, and the optimization is dependent on the number of data points and not on the number of dimensions. Okay, so I hope that this kind of gave you like a nice overview of the basic principles of support vector machines. I'm not going to ask like, oh, okay, like, can you come up with the dual form of the Lagrangian optimization or something like that. I think what the main reasons or the main ideas are, like why optimal optimal separation hyperplane, or like what's the optimal margin, why do we need that, what are the characteristics of support vector machines, and what are the hyperparameters that we need to think about and optimize for. I think I want like the concept of slack variables, I feel like is kind of important, as well as like what is the definition of a support vector, like what makes a support vector, what makes a support vector machine, the characteristics, okay, like what happens if the number of support vectors that I have is too large. Am I applying the right tool to my problem? Is my problem actually not linearly separable? Is my problem more complex than I allow my support vector machine to be? What can I do then? Like, oh, like I could use different kernels. I can play around with the number of these number of hyperparameters in the kernels, and so it's kind of like. I would like you to think about these aspects more than about the math behind the optimizations. Okay, and yeah, I hope that it makes sense now when you use it in the homework, and yeah, I think that one's due on Sunday, right? Yeah. And then we talked about. Quiz next week, Wednesday, March 1st, and that will include support vector machines, the neural network stuff, and kind of like everything, this unsupervised learning, kind of everything that we had between the two quizzes, and it's not going to be like super difficult again. Mostly concepts and ideas, maybe a little bit of a problem that you have to solve with, like, I don't know, a decision tree or a naive Bayes or unsupervised learning problem or something like that. and a few questions. And then what I would like to do for the second half of next week's Wednesday class is that everybody, or everybody's group presents a little bit like a 5-minute to 10-minute, maybe with some questions from each person, or each group gets a couple of questions from me and from the other students, so that we get rolling on the course projects that you will be then able to work on for 2 weeks. Li-Xing's going to be here. I'll be responding to emails if you have questions. Yeah, that's kind of it.
So this is actually from lecture number 2, but with probably approximately correct learning. I understand what it is, but I don't fully understand the purpose.
Okay, well, the purpose behind it is kind of like theory driven, so that the it helps you understand based off of like a theoretical framework that to achieve a certain accuracy with a certain high probability or a certain high certainty, you need X amount of data.
Okay.
So it kind of gives you like a framework, like, okay, so I have this problem and I think it's really hard, and it's really kind of costly for me to like collect data or like annotate data.
So it's like, what's the bare minimum?
Exactly.
Okay.
Exactly, and it's not going to give you like an exact number of data you need to find,
Okay.
but it kind of gives you like a ballpark. Okay, is it 10 data points? Is it 100, 1,000, 100,000, and so on.
So it's like you don't do all this extra work kind of thing.
Yeah.
For like marginal.
Right.
Okay.
And it certainly and it depends on my needs. So if I say, well, I only need to be 80% correct, it's because it's not that important that I'm like 95% correct all the time. So I need a lot less data then, as if I would need like a much higher accuracy. And but I want to you have to weigh that. So how accurate do I want to be? Do I want to be 80% accurate? That's one part. But then with how much likelihood do I want to be? So it's kind of tricky in the sense that if I want to be very, very certain that I find an 80% solution, the data point number goes up again. So it's kind of like this balancing act between how certain do I want to be about my solution being that accurate. And yeah, so the packed learning is just giving you a theoretical framework to think about these things, or to allow you to think about. And honestly, or unfortunately, it has limited practical implication.
Yeah, I think that was mostly the reason behind my question. I was I kind of understand what this is, but why?
Yeah, it's just a kind of like a thinking framework, so to say, or
So, do we have to turn in a project proposal this week, or?
Yes. That'd be good.
Is there
something?
are you gonna make a?
Wait, is there not?
Is there gonna be a submission online?
Oh, did I not put that up? No. I thought I did that with the homework. Okay.
Yeah.
When did we say that it's due? Was it also Sunday?
No. It hasn't been specified. I
don't think it has been specified.
Let's do it also Sunday.
Are you gonna work on it?
Also, reading assignments, I joined from week 3 and week 6. We have to write something because there's so many readings over there.
For a proposal.
Same as
You don't have to write anything, but just if you have questions about them, just ask them.
It's a big challenge.
I was planning to have like a question and answer session today, but then I
Right now,
realized that we haven't really talked
you've
about
seen it.
supported virtual machines yet, and so.
Because reading is kind of like, it's a lot and it's kind of hard, honestly.
Oh, that would be good, you can combine that
It'd be great
along
if you
with
can just
this.
talk like briefly.
Yeah, we
don't
should
think
have
we're
a
not sure.
discussion board
Yeah.
and a couple of questions about that.
Question and answer.
We can like talk about it on Monday. Let's reserve like an hour for that and talk about the publications. Do you use the discussion board for that?
I don't think anybody posted
There's
anything.
Everyone's posting. Everyone's kind of just asking right now.
Yeah, we should,
Yeah.
like.
Get together.
The assignment's
People
gone.
prefer face-to-face.
If any other quiz
Yeah,
questions
basically,
come up, do you
yeah.
prefer if we just start like a thread on the discussion board for
Yeah.
any, okay. And then that way we don't have to.
Yeah. Wait, that's not right. That's not right.
So these are all questions in regards to the project, right? You guys are ready to ask for the project?
Wait, everybody has questions because
I know.
I have to run to the bus.
I just wanted to know when the proposal
Yeah.
was due.
Sunday.
Sunday, okay.
Midnight.
Okay.
You get like 15 points. That's the yeah.
I joined a big data challenge. So can I use it
It's
as
a
a
slide.
project?
Oh,
Yeah.
yeah, today.
Sure.
Okay, thank you, appreciate it. Thank you.
And I want to check that, can you get the email from TA?
I work at.
No,
Oh,
the email that
He's
you
not
got,
part of the
thank
class.
you.
Yeah,
You're part of the class.
If
I mean, if
there's
you
anything
can,
else
if
that
you can
needs to be recorded,
make sure
so
that
you
he's
you
not
won't
doing
get
all the
the
work.
email from TA?
once in a while I do it, but not very
Just
often.
include
It's like on and off, quote, but yeah.
Yeah, because the TA sent the
And then,
email said that
like,
they
alright.
changed the homework
Right, because
to
that's
use
also
the C.
kind of
Oh,
the main
yeah,
thing.
Yeah, so I thought that you will get the
Oh, no,
email.
no.
Okay, then after that,
Okay.
I'll forward the email
Okay,
from
thank
TA.
you. Okay, thank you.
I have those two.
Thank you, guys. Thank you.
So I think it's kind of interesting.
So have you joined a team or?
No, I'm kind of like off, I'm kind of off in my own little thing, but it's more of a, my other school and this is kind of like combining, so it's a lot, it drains me a lot, but it's okay, I'm kind of like just in the background, trying to like getting it all and watching everyone else and recording it, so it's kind of like, I'm off in the background, but I'm listening and trying to pay attention, because it's a little overwhelming at times.
Sometimes I'm wondering that why you are always like
Focusing on this,
yeah.
because I wanna learn it, but yet I wanna catch up to the math as well, so I'm struggling, but I'm making it, it's all right,
Yeah. Sometimes I feel like you are already so busy, but why do you join other classes or other courses?
well, the other courses is because I have to complete, because of my masters, I get a better extension, so it's, I mean, you were complete your masters, right?
I'm already, this is my last semester, this is my master.
Okay, so this is your master. So that's where I'm still like in the process of getting into these things, so I'm in,
Probably,
I'm
but
in
I
that
don't
cycle.
get to do a neural network,
But,
because neural networks are the.
if I don't listen to, if I don't apply myself now,
they were the
I
first
won't
ones
be able
do
to,
this
that time will
tests
be
of-
wasted,
of,
that I didn't
Yeah,
try.
because I just want,
Yeah.
you know, it's
Uh,
5 lines of code, it's not that much work.
For myself, I prefer
That's
to
what I tried.
plenty of time for myself.
Yes.
Because that's been
Yes.
relatively quick, really,
I don't
it's a
like
small data set.
Attending the lectures, it's, yeah,
Okay.
unless it
But
is
we need
very
to sit down
helpful.
and write the
Yeah,
proposal.
well, hold on, let me turn it
and
on. But,
spec it, right?
Yes,
Okay.
yes.